Hello. In this session we discuss the behavior of an electric charge which is moving through a magnetic field. Here we consider the motion of the charge which is at an angle theta with the magnetic field. Now suppose Q is the charge having mass m. I am firing that into the magnetic field at an angle theta with a velocity v. This is the direction of the uniform magnetic field. Now after entering into the magnetic field, we can find that the particle is moving in a curved path like this, which is extending along the direction of the magnetic field. And this path we call helical path. Helical path. Now why the particle is turning around? Because according to magnetic Lorentz force, we find that the force is of the form Q into V cross V, where the particle is experiencing a force F which is perpendicular to the direction of P. So when the particle is trying to move like this, a force will be acting perpendicular to that particle is taken to bend like this according to the force. So that is why the particle is taking turn around. But why it is going in this particular fashion, going around, it is because of the balancing of centrifugal force experienced by the particle with the magnetic Lorentz force. That means for this particular case, we can have the velocity derived or resolved into two. This is v sin theta, and along this particular direction there will be v cos theta coming. Now this v sin theta is responsible for this force, and this v cos theta is simply dragging the particle along the direction of the magnetic field. So magnetic Lorentz force is making it to turn like this, but this v cos theta is taking the charges to go along this way. So together it forms a helical path. So for this particular case, the force equation will be m into v sin theta the whole square by r, centrifugal force, which is equal to q into v sin theta. This is the condition for going around. Okay? Now we apply a special case over here that suppose the particle is entering perpendicularly into the field. Suppose the particle is entering perpendicular to the field, what happens is that theta becomes equals 90 degree, and therefore the formula becomes mv square by r equal to Q into V into V. Now in this particular case, what happens is, for this V cos theta becomes 0. That means the particle, instead of going like this, instead the particle will be moving in a fixed circular path like this. It goes around in a fixed circular path of definite radius r. Now that r we can find out from this one, that the radius of the path r from this one will be equal to m into v divided by q into v, or equal to momentum p divided by q into v, or else we can write this as root of 2 into m into kinetic energy divided by q into v. These are the three different ways in which you can represent the radius of the circular path followed by the charged particle when it enters perpendicularly into the field. Okay? So as the motion is a repeated motion, it's not stopping, it is going around again and again. You can find that it's a periodic motion, that it must be having a definite time period and also definite frequency. So that also you must get from this equation. That is, the equation for time period. Equation for time period we can get from the definition. It is the time taken for one complete rotation, that as it goes around in a fixed circle like this, for one complete rotation it is traveling through the circumference with a velocity v. Therefore, time period t will be equal to distance traveled by velocity. And you will find the equation for r from here, and substituting, you will be getting this as 2 pi by v into m into v divided by q into v. Therefore, this v and this v cancels, and you get the time period t equal to 2 pi m divided by q into v. Very important equation. If time period is this much, then the frequency of the particle will be frequency of the particle nu. Frequency nu will be equal to reciprocal of the time period, that is q into v by 2 pi m. Now you see that time period and frequency is not dependent on the radius or the speed of the particle. Instead, it is found to depend on the type of charge and the magnetic field. Okay? Very important. And one more equation you are supposed to remember from this part is kinetic energy of the particle in the magnetic field, as it is moving in the magnetic field. So kinetic energy can be taken as half mv square, kinetic energy Ek, half mv square, and we substitute for v from this equation, that v equal to, that is half m into v, how much is r equal to m into v by q into v, and therefore v equal to r q v by m. This you can substitute over here as r square q square v square divided by m square, and therefore kinetic energy Ek will be equal to half into q square v square r square divided by m. This is also you have to remember. So equation for radius, equation for time period, equation for frequency, and last one, equation for kinetic energy of the charge particle. while discussing you can find that, or you might have noticed that the force F is acting perpendicular to the velocity. That we found. Or perpendicular to what you say, the radius, and therefore the force cannot do any work on the system. And therefore, the kinetic energy of the charged particle should not be varying due to the effect of what you say, the magnetic force. Okay?